Let's look at one more function and see if we can find the inverse of this function. Here we have the function f of x equals x squared plus 4. Remember, to find the inverse, first thing you do is replace f of x with y. Now, interchange the x and y and solve this new equation for y. So the first thing I'll do is subtract 4 from both sides. And now, to solve for y, I need to take the square root of both sides. Well, remember, as soon as I take the square root, I have to account for both the positive value and the negative value that will give us the y value. So immediately when that happens, from what we've learned about functions, this expression, this equation, does not define a function. Because this shows us that for every x value that's in the domain, that would produce 2 values for y. If we let x equal 8, 8 minus 4 is 4, square root of 4 is 2, so when x is 8, the y value has 2 different values. Y is positive 2 or y is negative 2. And so one value of x is paired with 2 different values of y, which violates the function rule. So even though this is the inverse, of our original function, it is not a function. So here's our first example of a function whose inverse is not a function. And that's the case. Not every function, when you form its inverse, will that inverse also be a function. Here's a perfect example of that. This expression does not define a function. In fact, functions whose inverse is a function are given a special name. They're called one-to-one functions. That idea of one-to-one, only one value of the domain is only matched up to one value of the range. And you'll never have 2 values of the domain that match up to one value of the range. That's what we have here, don't we? Don't we have 2 values of the domain that would give us the same range value? If we let x be 2, in the original function, 2 squared is 4, 4 plus 4 is 8. If x is 2, y is 8. But if x is negative 2, the square of negative 2 is 4, 4 plus 4 is 8. 2 values of x map to the same value of y, which is okay to have a function. You just can't have it the other way. You can't have one value here mapping to 2 values there, which is what the inverse would give us. So in this case, the inverse is not a function. And if you think about the graph of this particular function, this is a parabola that opens up, isn't it? And it's been shifted up. It's been shifted up to the point 0, 4, has it not? Isn't that true? And what's interesting about finding the inverse, we've talked some about symmetry. We've talked about symmetry with respect to the y-axis. That's what this graph exhibits, is symmetry with respect to the y-axis. If you want to find the graph of the inverse of a function, its graph is symmetric with respect to the line y equals x. So every point here has a symmetric mirror point over here. And so what you end up with is the parabola that looks like this, which we know can't be a function because it fails the vertical line test. And that actually gives us another test, to test a function to know whether or not its inverse would be a function. If the function fails the horizontal line test, 2 values of x give us the same value of y. If it fails the horizontal line test, its inverse would fail the vertical line test. So one-to-one functions, which have an inverse that's a function, they will pass the horizontal line test. Functions like f of x equals x squared plus 4, whose graph fails the horizontal line test, the inverse of that function is not a function because its graph would fail the vertical line test. So a lot of interesting things going on here. When we look at functions, try to find their inverse. Sometimes the inverse of a function is a function, sometimes it's not.